Let's play with some slime.
Hey Daniel, what you doing?
I'm playing with slime.
What's slime?
It's stretchy stuff, and you can touch it.
Oh my gosh, that looks amazing. So, what are you doing with this?
I'm playing with it.
Show me how you stretch it.
Oh.
Whoa, I thought it was a liquid, and it's like goo. Oh, you know what that reminds me of?
What? Boogers.
Ew, not boogers. Okay.
Green boogers.
So, you're playing with green slime, right?
Yeah, I know it's like boogers.
Okay. Well, did you know that what this actually is called a polymer?
Polymer?
Yeah, a polymer. And it's made out of lots and lots of monomers.
Nah.
Exactly. Hey, I got a question for you.
What is it?
Do you think these kids want to know how this stuff is made?
I think so. I want to come how.
You want to know?
Yeah.
All right.
From my nose.
No, not from your nose. We're not going to make boogers. We're going to make polymers. There's a difference. Are you ready to show them how it's done?
Yeah.
All right.
A booger.
No polymers. Let's go. All right. So today we're talking all about polymers. Now, as you saw Daniel playing with earlier, he stumbled into a very fine example of what a polymer is. This slime is a very great example of a polymer. Looks and acts kind of like a liquid at first, but as you begin to explore its properties, you realize it can be stretched and pulled, but it doesn't break or snap. It's very much elastic. And we're going to talk about what gives it that special property. Polymers are something that you should be very familiar with on an everyday level. They handle everything from natural things like cotton. In our natural world, this is grown and used as industrial properties to make things like clothing. We also use them in the laboratory. We synthesize or create new things that are polymer-like into very useful tools that I used to use a lot, like rope. Rope, like this, is made of polymers. Polymers, again, are very strong. They can hold a lot of weight. They can be stretched and pulled without hopefully breaking. And if we take a closer look, which we will, we're going to see it's made of tinier and tinier and tinier threads of rope. And it's very much, with these tiny little hairs here, just like our slime. And now it gets stretched and pulled and very thin, but enough of it looks very cohesive. So we're going to take a deeper dive into polymers today. Now remember, we're still dealing with carbon chemistry. The carbons that we talked about last week on Thursday, the hydrocarbon chains that we were talking about, from the saturated versus the unsaturated, the hydrocarbons, we're still going to be continuing that conversation. And we're going to look at new useful ways that they're built, both by Mother Nature and by humans in the laboratory. Come on, let's go take a closer look. All right, so before we get into the actual chemistry with the atoms and molecules and compounds of polymers, let's talk specifically about what makes a polymer a polymer. And as you can imagine, I want to use an analogy here. Now, the first thing that we're going to start with is a simple one unit, one thing that is identical to another thing. In this case, I'm going to use a carabiner. Now, this carabiner has the same shape and color structure as, say, this carabiner. Now, in the world of chemistry, we would call these monomers. Now, think about the word monomer. Monomer. Mono meaning one, okay? And as this one molecule, essentially, and if this monomer were to attach itself to this monomer, all of a sudden, we start what looks like a chain. And as more monomers begin to attach themselves, you begin to get this long, lengthy line of them. And now we have a polymer. We have many, remember poly means many, we have many molecules connected in a chain-like structure. And this is going to be, as we've talked about before, a very good stronghold into understanding how things are made in long chain links. Again, just like when we introduce things like our slime and these long chain links that can stretch thinner and thinner and thinner, and how long they go all depends on the structural shape of their monomers collectively tied into polymers. So we start off with the idea of what a monomer is, and the monomer is going to come together collectively to create a long chain link that we call a polymer. So remember, mono means one. Mer, it comes from the Greek, its root base is in molecule. So one molecule connects together to make a polymer, which is many molecules, and we chain link those together. That's going to be the basic structure that we're talking about today. So let's look at real world examples of these as we dive into the absolute chemistry behind it all. All right. If we're going to have a deep understanding of what a polymer is, we need to understand that polymers come in two flavors, meaning two types. One type of polymer is going to be your natural polymer. These are the things that we find all around us. Good old Mother Nature makes those available for us. The other type of polymer is something we can produce in the lab, a synthetic type of polymer. And today we're going to first focus on synthetic polymers. But these two have a very mixed story, and we're going to learn a lot about it when we first start to talk about our first synthetic polymer, which is rubber. That's right, rubber. Rubber became a synthetic polymer only after it had a necessity from its natural predecessor. Let's take a deep dive into rubber. So one of the best ways to think about rubber is to get a good firm look on it. This is one of my hiking boots. It has a synthetic sole on it. The synthetic sole is a rubber sole. Now, this type of rubber you probably have on the bottom of your shoes, and almost every shoe in the world probably has some resemblance of this on it. Now, it's synthetic, but here's the catch. It wasn't always the case. See, rubber actually is the sap that comes out of the rubber tree. Now, that means that rubber started off as a natural polymer. And see, the problem with where rubber grows is that it needs a tropical climate. The rubber tree, that is, needs a tropical climate. It needs a place where the rubber tree can flourish. It doesn't do well in temperate climates, but a nice tropical, lush area, usually rainforests or thick jungles, are going to be where you're going to find rubber trees. Now, the world did not have an exceedingly large market for rubber until all of a sudden World War II breaks out, and the Allies realized that they needed rubber for lots of things, including boots to put on soldiers. And what they realized really quickly was that most of the natural polymer rubber and rubber trees were growing in places that they no longer had access to, and therefore were cut off from their natural supply of this polymer. The chemists for the Allies had to quickly figure out a way to synthesize to create a synthetic alternative, and they did. In that synthesizing of rubber, we also found out that some things like vulcanization could be done to it, in which case you could take a soft rubber, apply a certain amount of thermal energy, heat, and in this process chemically break up the polymers back up into their monomers and then reconfigure them into longer chains that had a higher density of carbon in them. This is a process known as vulcanization, and that, my friends, is how tires are produced now, because tires on the road typically are going to have a higher density than, say, the rubber on most shoes or boots. So there you have it, the story behind rubber's naturally occurring polymer that out of necessity became synthesized into one of our first type of synthetic polymers. Rubber is a synthetic polymer. All right, so we have rubber now as a synthetic polymer, but remember, it originated from a natural polymer that we wanted to create something in the lab to duplicate it or to replicate it. The next story is not too far off from the truth. In fact, this story starts in the 1930s with a scientist who was looking at the natural polymer of silk. Silkworms make a very strong type of material, but because of its limited availability, again, silkworms can only make so much silk. And when you ramp up production of, say, different materials that are requiring this, we needed an alternative. So we turned to the scientists to synthesize the natural polymer of silk. They did it with probably my favorite synthetic polymer, and that is nylon. Now, why, might you ask, is nylon my favorite synthetic polymer? Oh, I'll tell you why. Number one, it keeps me safe every time I go climbing. Now, this climbing rope, as you saw in the beginning of the video, I introduced as a type of polymer. Now, the rope itself is stretchy but strong to a point. Now, when we look deeper inside of this rope, what we see is that inside this sheath, this woven sheath, there's actually a core of rope. You peel it back, and you'll see that it's a core of nylon. And in fact, this whole core is made up of tinier cores, and each of those cores is made up of tinier cores, and each of these is made up of thousands upon thousands of individual, very hard to see, teeny tiny little hairs, which are polymers that are synthesizing what silk would be. We just call it nylon. And this is what makes this so strong. It's like taking, more and more and more ropes, wrapping them, binding them until you have something visibly incredibly strong and very durable. Now, it doesn't end there. The majority of people in the safety equipment industry use nylon all the time to make sure that they are safe. I not only used it in this format, you could also look at it in this format. It can be shapen into different things. This is what we call tape webbing. This type of webbing can be folded up into its own long chain, but if you take the end of it and pull it, now you've got another long strip of something, nothing more than nylon, a synthesized version of silk. It's shiny, it's slippery, but it's very strong. And when it's woven in a way like this, it can do different things to help protect people in places where they need higher safety. Now, it doesn't end there, of course. Maybe you're an avid fisherman. I know some of you are. And if you are, you like to catch fish, and you probably use fishing line to do it. This fishing line is very thin, it's translucent, it's light, but it's strong. This fishing line is incredibly strong. In fact, this particular fishing line says it will hold 12 pounds of test on one single strand. That means it can stretch and thin without actually breaking. That's what makes this fishing line incredibly durable. And why do we get it? Because we synthesized what was silk and turned it into nylon. Now, of course, I'm going to end on a very relaxing note with nylon. One of my all-time recent favorite pastimes has been using something like this. You might have one at home yourself. It's your handy-dandy portable go-to bed. It's a hammock, right? Now, this material is nothing but nylon. It's woven, it's strong, it stretches, but it doesn't give or break. And in enough material sewn together, you can have a very relaxing sunny afternoon to take a nice little cat nap right after science class. So let's take the final synthetic polymer and really dive in deep, because I think this is the one that everyone, regardless of the first two, even though they are very prolific in your lives and we use them all the time, this is the one that without a doubt has a major impact to your everyday life. This one is a polyethylene. Now, poly, again, as we know, and then ethylene, you might remember, is the double bonded molecule of carbon that came together from our last lesson. So In this case, we've got ethyl, which was C2H4. Its double bonded carbon atoms are linked together from that one monomer into a polymer. And what this does is adds rigidity and strength. The more carbon chains you have, adds more rigidity and strength. But something super cool about polyethylene, and it's a generic name. Realize that I'm talking about, there are many different types of ethylenes. There's, polyethylene, you've got methylethylene, you've got versions of countless types, and you'll see why here in a second, that it goes so prolific into how many different flavors of this you get, because what we're talking about here essentially, folks, is plastic. All the different variations of plastic. Now, one of the first uses and discoveries for this was going to be laboratory based. And by what I mean by that is once it was discovered, and these things are formed by pressure typically, not by temperature, by pressure, forcing the monomers to bond with one another. All of a sudden, you've got something that's very much like this. This is a plastic bottle, a chemical plastic bottle, and its contents inside are caustic. You could use glass, but glass is fragile and expensive. And when we use glass, those properties don't allow for it to be jostled and juggled around very easily. Now, you don't want to do that regardless because you're dealing with a chemical here. But at the same time, accidents happen, and glass increases the amount of accidents that could and would happen if, say, somebody were to drop this. But this plastic container, this polyethylene container, was formed in a synthetic way to not only be very rigid and flexible, much more resilient than glass, but here's another key property that glass doesn't have. Polyethylenes, or plastics, are non-polar. That's right, polarity. It doesn't have a charge net on either side. Remember, water was polar charged. And certain chemicals that you put in these containers are polar as well. What it means is they're not attracted to anything inside these plastics. And in fact, if you go into the history of plastic containers for chemical uses, you might cross a very familiar name, and that name would be Nalgene. Now, this particular Nalgene bottle, made for consumer purposes with cute colors and nice, much more rigid than our predecessor bottle here, but its roots are in chemistry. This company originally was founded and created for containing and using plastic polyethylene jars to hold chemical compounds in. That's what their manufacturer's purpose was. They were adopted by a company called Flynn Scientific, which, if you look here, is this name brand company that sells chemical products, and these plastic bottles are useful in containing it. They also found out that they are very food safe. If they're good at keeping chemicals from sticking and adhering and bonding with plastic inside of here, then they're probably good at keeping you safe so that when you drink out of these, none of the plastic byproducts adhere to the water and become ingestible, which could become toxic. They've done that by generating a very specific type of polyethylene. Remember, many types of ethyls bonded together in a polymer chain from the original monomer. That sounds like a big mouthful, but remember, it's no different than at the beginning when we talked about the monomers being the different carabiners linking together to make a chain. And however long that chain is, or however dense that chain is with, say, carbon, that's going to make this more rigid and strong. Now, another useful way to do this, and what looks incredibly different, but very familiar, might be your every ordinary day milk jug. The plastic container that is holding on to this is given its way to being a polyethylene. Now, that's really great because it keeps our food safe, it keeps our food consumable, and it allows for it to also have rapid temperature changes. You think about it, you keep this in the refrigerator. And to be in the refrigerator, it doesn't change by taking the temperature down lower. Any kind of chemical process to where it might become brittle or rigid, it's still flexible and pliable, and it still has the same non-polar attributes that we want it to have to keep our food safe. Now, last but definitely not least, one of my favorite types of polyethylene that I've really become accustomed to playing with in the past few years have been...
I don't like confrontation.
Oh, don't worry, Rex. We'll get you through it, buddy. So, toys, right? Toys. The majority of toys today are made from a very safe, recyclable polyethylene, so that when little kids start to put toys in their mouth, it doesn't come off as caustic or dangerous. That's what makes...
Do you know what I love?
Is it chemistry? Oh, it's riddles. I thought it was chemistry. But that's what makes these toys so much fun, but they're also very safe and durable. And don't tell Woody, but I found his hat. Okay, before we step over to the natural side of things, I wanted to take a brief second to talk about your things that bind stuff together. These different liquids, glues, epoxies, polymers, they're all made of monomers inside of them. Now, they've been injected with specific types of monomers, and surrounding them are these different chemical stabilizers, these things that will not allow the monomers to bond unless, say, they're exposed to oxygen. This is why they always say make sure you keep your lid down, because if you don't, oxygen gets in there and allows the monomers to start to create these long chains of polymers that essentially bind the material together. And in some cases, that happens really quickly. Now, essentially, with the material, you're going to make sure that it chemically adheres to it. And that's what these are doing. They're trying to bond different materials together. And I wanted to make a brief statement about that, because in fact, inside of here are just a load of monomers waiting to get out. And once they do, they'll be exposed to the air. Chemical reaction will occur between the two materials that you might be trying to bond together. In this case, maybe wood glue, or in the case of the super glue, from right up here where my glasses broke this weekend, that I'll have to be able to bond them back together with something a little bit stronger than wood glue, so then this will adhere, say, a polyethylene, the plastic frames, back together. And it does a really great job. So far, so good. Just wanted to put that in there before we move on over to our natural polymers. But let's do that, shall we? Now let's step over here to the natural side of polymers. Natural polymers, as you might suspect, are going to take us way further down that road, tiptoeing ever closer towards biology. But to get there, we need to know what type of natural polymers there are, and we need to understand what makes them, because this, my friends, is going to start the essence of life. And it all begins with everybody's favorite delectable little treat, sugar. Now, sugar, as you see here, is table sugar. It's what we would call sucrose. Sucrose is something that's been built up. Go back to thinking about the rope, right? The thick rope, how it was made of tinier ropes, and those ropes were made of tinier ropes and tinier ropes. Well, essentially, sugar can do the same thing. And that's how we synthesize these kinds of things. Sugar comes from your basic everyday glucose. Now, you need glucose in your body. It's a simple sugar. Its base formula is C6 carbon 6, hydrogen 12, oxygen 6. That's your basic glucose. Now, glucose as a monomer can start to bond with other glucose molecules, building up to what you see in this jar here, which is sugar, what we call sucrose. Not glucose, but sucrose. It's more complex. It would have sucrose, and that would be C12H22 or 23, depending on if it's manufactured or not, O12. And in this case, what we're looking at is a higher density, obviously, everything's doubled if you notice, from our glucose, a higher density polymer. But Sucrose can also act as a monomer on its own. And when it begins to wrap around other sucrose molecules, everybody's joy to deal with is fructose. You get fructose, and that's what makes Coke so sweet. We say there's sugar in there, but the high density sugar that is in here is high fructose corn syrup. And that is where we lead into what we're talking about here. Notice I said corn. Corn is naturally occurring plant-based materials that builds its own polymers. And the way it does it is through the sugar molecules, photosynthesis. We'll get to a little bit of that next week. But to understand it at its core, you start off with basic glucose. You build that glucose into sucrose. That sucrose gets built into fructose. And from there, these are all classified as our first natural polymers, which are, let's see, on our natural side, they're starches. A starch is your first natural polymer. Every time you see trees or plants with their roots, all of those roots are bound up and wound up from starches, all of the sugars that are produced inside of them. Now, interestingly enough, if you think of something like wheat or corn grounds are ground up and turned into a meal. Okay, you dry them, you grind them up, and you turn them into wheat or cornmeal. And these flours that we get from them, not flowers like blooming, but I mean like the powdery flour that you might make bread out of. All that is ground up starches, which we can then contribute into adding more polymers to. So let's take a step back real quick. I need some more board space. I'm going to write this out bigger. Let me just do that real quick. I said real quick, hold on, give me a second. Now isn't that better? Let's keep going. So we've got starches. Starches formed from sugars, essentially acting as monomers, building themselves up into bigger polymers, which then act as monomers, building themselves into more complex polymers. I think you get the idea here. As we get bigger and bigger and bigger sugar polymer molecules wrapping around each other, what we're actually starting to classify these as is something you're probably familiar with in the study of diet and dietitians. We call these types of sugar starches carbohydrates. And carbohydrates, the carbon and the hydrated, go down here, are essentially carbon with hydrogen and oxygen, a hydrated molecule, water essentially. Carbohydrates are defined as these bigger and more robust sugar molecules wrapping around each other, which are all generically classified as starches, which are our first foundation for understanding natural polymers. Plants do this. You and I do this. This is not uncommon, but we are very familiar with this through biology, not formally yet, but also just in our every ordinary day lives. You eat foods that contain starches. You understand plants form from starches. Think all the way back to 6th grade and you would have remembered something to do with how plants, through photosynthesis, take sugar, turn it into energy, and build starches. How do they do it? They take simple sugars, taking from monomers, turn them back into polymers, back into monomers, building themselves up again and again and again until you get these nice, robust carbohydrates, which we use, again, as fuel. So, now that you have a firm foundation for what a starch is, how it's made, and what it produces, let's move on to the second type of natural polymer. Wow, that's pretty awesome how starches have done all this to make carbohydrates. But our next natural polymer builds where that leaves off. If you take a carbohydrate and begin wrapping more and more glucose around it, you're fortifying it, you're making it much more rigid, much more resilient, and you actually even make it undigestible. And in fact, this next natural polymer takes starches, turns them into carbohydrates, and then wraps it around themselves even more robustly and densely, and we get what's called cellulose. Now, cellulose looks like this. That's right, it's wood. Wood is a type of cellulose. And one that you might actually be familiar with too is this. We saw at the beginning of our video, cotton. Now, you can't eat a cotton ball, and I wouldn't recommend it even if you wanted to try, because you can't digest it. Pure cotton, and in fact, things that we weave out to make materials of for fabrics and things like that, they're done so in such a way because they have a hard time breaking down. Why do they have a hard time breaking down? Well, it's because they're built on carbohydrates wrapping themselves around other carbohydrates, which are already dense and robust sugars or glucose essentially. And in fact, most things like cotton that are natural forming cellulose are built on chain links that are over 3,000 times bigger than glucose itself. And that's how we start to identify what is cellulose. An undigestible, hard to break down, naturally produced fiber, and that's what these are, remember, just like our slime is sort of like this elongated, stretchy, chain-linked fiber of a polymer. That's what these are too. They just, for our sake and purposes, are undigestible, but they happen naturally, and that's the key here. It's still building off of sugar molecules forming glucose, and those glucose building up more and more and more robust polymers until we get to this level, which is cellulose. All right, let's transition to more chemical biology with the next natural polymer. Okay, this is the third of the fourth type of natural polymers. We've got nucleic acids. Nucleic acids are very familiar to you. They make up who you are. They make up what every animal is, what every plant is, because they're the backbone of essentially the playbook to make every cell possible. That's right. You're probably thinking about it right now. There are two types of nucleic acids. One is called RNA, and that's ribonucleic acids, and the other one takes two RNAs and zips them together, and we get DNA, deoxyribonucleic acids. Both of these together are the information carriers. They have a spine of these deoxyribose sugars, all right? So you get these deoxyribose sugars aligned together, and they are chain linked. Why? Because they are polymers, and spinning off of each of them are different types of information nucleic acids, which would be things like there's A's and G's and C's and T's, and they match up accordingly. The other side, it's a lot of voodoo science, and that's what I'm going to save for next year. But these DNA and RNA molecules come together with these different amino acids on the side to bind the two types of nucleic acids together. And with these new amino acids, they carry the code to make a blood cell, and to reproduce it, whether it be a white blood cell or a red blood cell. They might reproduce to say, hey, we need another hair follicle cell. Or sometimes they don't. It just depends. But you get the gist. DNA is at the heart of who you are, is at the heart of who I am, is at the heart of what makes a plant, and what makes an animal an animal. It's the coding the genetic means to be able to reproduce at the cellular level, all based on natural polymers that are either RNA or DNA, and they connect these sugar chains together to make these nice amino acids bind in a very specific way. Now let's see the last part of it, which is what these these nucleic acids can actually make. And you're going to be surprised when you see it because it's extremely familiar. Let's slide this over and bring it back up onto the board. Here we go. Here it is. We end with proteins. They are the last of 4 types of natural forming polymers. You can probably imagine you've heard of proteins before. Proteins are built on a massive chain of over 100 different amino acid monomers connecting themselves together in a long chain link to do a myriad of things. Proteins are building your muscles. Proteins are building your hair, if you're lucky. Proteins are building all amazing things that make you grow and make you strong, and they are built on the backbones of polymers. Again, they start off with either a carboxyl group, and all that is a hydrocarbon. So take our 2 carbon atoms. Whoops, that one's running out. 2 carbon atoms, double bonded, let's say hydrogen. But let's say one of these hydrogens doesn't bond here, and let's say we bond it with an OH molecule instead. This replacement that's adding to it is a functional group. It changes the function of what this is. And in changing that, they turn themselves into different things. Maybe a nucleic acid. In this case, for proteins, they're amino acids. And these amino acids is just a fancy way of saying the type of monomers that link themselves together to make a polymer. And we call those proteins. They're made of over 100 of these different functional groups, either carboxyl groups. And what we get are proteins. This is, as you can start to see, proteins are made of hundreds of monomers that make polymers that you know can go into your muscles and make you stronger. And nucleic acids, which are giving the instruction to build the proteins in the first place, are coming from RNAs and DNAs, which are long sugar chain molecules that in themselves are giving the instructional code to build you. And then from those sugars, we can also talk about cellulose. And now for plants, cellulose is a wonderful thing because it gives them rigidity and structure. It gives trees trunks and wood, and it gives plants fibrous materials like roots to grow and hold strong into the ground. But once we take them from there and we back it up, we get the starches. And all of this wonderful world of polymers that are naturally occurring are coming from basic sugar molecules. Think how amazing that is. So the next time you drink a Coca-Cola, that high fructose corn syrup in there, or the next time you sprinkle some sugar just to add to your cereal, think about that this is the basic building block of natural polymers, and that we as a human being can learn how to synthesize that into our synthetic polymers that we talked about, all the rubber that we talked about, all the nylon we talked about, all the polyethylenes we talked about. And we've turned this world into something that we can celebrate and know that we can effectively create positive changes for. At the end of this video, there's going to be another video in the folder. It's a crash course chemistry on it. It just adds to the pile of interesting things, especially about synthetic polymers. I didn't want to lead with that one because it's a little of the bio-heavy forward stuff. But for those of you interested, fascinating stuff. You should check it out. It's just another 10 minutes. It's not required, but I'm putting it there just to help you out. There's also another video that I'm adding. If you're a big fan of how stuff's made, I love that show. It's amazing. They do a wonderful expose on plastics. Again, another synthetic polymer. And they've got one on rubber as well. But I'll add those videos in the folder underneath your homework assignment, which is coming up immediately following this video. A few simple questions just to cover the topics. To put it in a nutshell, we're talking about polymers today, both natural, as we've just finished talking about, and the synthetic kinds that we had over here. And remember, there's 3 types of the synthetics, 4 types of naturals, and from that we get a really firm foundation to jump into later on this week on Thursday, where we're going to pick up with all of the natural types of processes that we can gain from this and start to really peek behind the door of biology and see why all of this is really connected. So, I hope you learned a lot. I hope you understand how all of this works, and I'll see you on the other side of Thursday when we get to that lesson as well. So until then, enjoy the rest of your day. Make sure you get your homework done next, and then enjoy some of those other videos. If you have time, I highly encourage you to see it, because it's still about how this world around you is so wonderful, majestic, and how people have been creative enough to synthesize things from the natural world so that we don't overexpose our resources and we keep them in check, including things like polyethylenes that can even be recycled. All right, gang, it's been a great time. We're finishing up with our polymers. We've got one more lesson to go as far as our natural and synthetic worlds of carbon chemistry are to be, and we'll round that off on Thursday. All right, until then, I'll see you then. Remember, as always, you are surrounded by people that love you, and always know that you're loved. What was the fun part?
When you pushed me down.
When I pushed you over like this?
Let's do that again.
Okay.
It was fun.
All right. Show me your boogers. That's not your boogers!
Oh,
You know what we're going to do today?
What?
We're going to teach the kids
how slime comes from.
where slime comes from. Okay, so that wasn't the most graceful entrance. Let's try it again. Interesting. Hey, you know what? You just stuck your finger in that. That is disgusting. There you go. I'll give you some more. Hey, you know what we should do?
What?
We should teach the kids how this is made. What do you think?
Yeah, we should.
Do you think they'll like learning all about the slime?
All about my boogers.
Ew, not your boogers.
It's stretchy. You see?
Oh my gosh. Okay.